Assalamualaikum. Let's start lecture 44. Chapter 8 we were discussing principal stresses under given loading. Previously we discussed about the principal stresses in beam. Then last lecture we discussed about design of a transmission shaft. Now this final topic we will discuss about stresses under combined loading. So if you have combined loading, so what will be the principal stresses and what will be the maximum shear stress in that case? Okay, let's see. Suppose we are a machine member, mechanical member or component or some mechanical structural component under arbitrary loading as shown over here. So we are interested what are the stresses at some specific location. For example, we are interested what are the stresses at K or H. So what we will do first, we will pass a section through points of interest, let's suppose over here, and we remove this section or this section depending on how you are working, and obviously we will define some coordinate as well. Now what we will do, we will determine the force couple system on that section interest of our interest, and that must balance the equilibrium. Means this F4, F5 and F6, the effect should be calculated over here, and that must be under static equilibrium. So it must maintain static equilibrium. Okay, so these forces can produce moment about z-axis, moment about y-axis, moment about x-axis, that will become torque. That can be a force. The force can be compressive or tensile, that P force, and we have a shear forces as well, Vz and Vy. Now in this case, this system consists of internal force, 3 force component and 3 vector component. Okay, not necessary all these 6 component will be there, but depending on the loading, these component can be present on the centroid of the section we are interested to find the stresses. Okay, now obviously this moment about z, moment about y, and that moment about x, these are the 3 moments. And then we have a force, normal force, that can be compressive or tensile. We have a shear force acting parallel to this surface, Vz, and Vy also a shear force. So we will determine the stress by applying superposition principle. Means the normal stresses will add and the shear stresses will add depending on how they are acting, what are the direction of those stress tensors. Now the axial force, if we consider only axial force, so we have, let's suppose, the point K and H we were interested. So this axial force P and the moment about Y and moment about Z will contribute to normal stresses that will become sigma x. And the shear component as shown over here, so that is torsion, Vy and Vz, these are the shear stresses that will produce shear component, these will produce shear stresses, and those shear stresses will be tau xz and tau xy. Now the complete state of stress at point H will be sigma x in the shear stress, and in K will be also the sigma x and tau xy, the shear stress. Now these stresses can be compressive in nature, or the tau will be, the direction can be reversed. Now the normal stress and shearing stress will use to find the principal stress, maximum shear stress, and orientation of principal plane. Now we will use this method, the principal stresses. So we know that the principal stresses we can find, that will be sigma minimum or let me write not minimum, let me write sigma A and B. These are my principal stresses. Sigma A will be simply sigma average plus radius, and sigma B, the second principal stress, will be sigma average minus radius. So in this case, sigma average will be sigma x by 2, and the radius will be simply sigma x by 2 square divided by tau xy square. So in this case, now if we have a component of sigma y as well, so in that case the average and the radius value will change, and the principal stresses, the maximum minimum, will be depending on the nature of principal stresses, and obviously the sigma c is 0 because it's a state of plane stress. Now these value combination, that analysis is valid in the value of maximum principal stress and the maximum shearing stress and orientation of principal stress. This analysis is valid only extend that condition of application of superposition principle. So what are the superposition principle? That stresses with an elastic limit, elastic and proportional limit, and the deformation are very small. So these are the condition we are following. We also discussed in previously when we apply method of superposition, especially for the statically indeterminate structure, and also St. Venant principles are met, means we are evaluating the stresses away from the load application point. So that's how we can find the complete state of stress and the stresses at the principal stresses are maximum shear stresses at different location. Now let's see an example, a sample problem. We have a 3 force are applied to a short steel post. So we have a steel post maybe joined to some mechanical component or structure or something like that, and it's the loading is shown, right? So this is this is x-axis, my y-axis is upward direction, and these are my y-axis, and this is my z-axis. The 30 kilonewton force acting parallel to x-axis at point D, and 70 kilonewton force is acting parallel to z-axis at this point A, and point B, the force of 50 kilonewton is acting parallel to y-axis, and the distance are given as well. Okay, now we are interested what are the principal stresses and maximum shear stress at this location H, point H. So that is 25 millimeter from the centroid of the section as shown over here. The section, if you take a section, that's a rectangular section. So what we will do, first we will find the internal forces in section EFG. So we will take a section over here at EFG. We will cut it, remove the upper portion, and we will transfer this force at the centroid of the section. That will be our internal force moment system. Then we will evaluate the normal stress at H, because it will causing some normal stress as well as it will cause some shear stress. Okay, and then we will calculate principal stresses based on those normal stress and shear stress. Okay, now what we will do, so what we do, we take a section at EFG, right? Now we have a shear force Vx along x-axis 30 kilonewton. We have a shear force Vz, that is 75 kilonewton, and we have a normal force acting perpendicular to this area EFH, that is 50 kilonewton. Now this 30 kilonewton multiplied by this distance 100 millimeter, that will produce moment about z-axis, right? So that moment about z-axis will be 30 multiplied by 0.13 kilonewton meter, and this force 75 kilonewton multiplied by 200 millimeter, that will produce moment about x-axis. Right? And also this 50 kilonewton multiplied by 130 millimeter, that is also produce moment about x-axis. So if you're looking at the x-axis, applying the thumb rule, right-hand thumb rule, so that 75 kilonewton will produce clockwise moment, 50 kilonewton multiplied by 130 millimeter, that will produce counterclockwise moment. So mx will be 50 kilonewton multiplied by 1.3 minus 75 kilonewton multiplied by 0.2 meter. So that will become 8.5 kilonewton meter. My, there is no moment about y-axis, it will become 0. So now some section properties. Area 0.4 multiplied by 0.140, 140 by 40 millimeter, the section is given. So moment about x-axis, we need to, what will be the Ix, 1 by 12 bh cube, and moment about z-axis, that we need Iz, so that is 1 by 12 bhq for that. These are the section properties. Now at point H, there is a shear stress due to Vz, there will be a normal stress due to P, there is normal stress due to Mx, and there is normal stress due to Mz, and then those nature of stresses we have to see. But due to Vx, there will be no shear stress because it is lying at the top surface. Vx is acting in this direction, so top and bottom surface with respect to Vx, the first moment of area will be 0, and that's why there is no shear stress due to Vx. Now sigma y-axis, sigma y is the normal stress, p by a, that is normal stress. Now mz, so mz at H will produce tensile stresses, and mz will produce tensile stress, and mx will produce compressive stresses. This should be mx. Okay, so there's a typo, so this is mx. So mx will produce compressive stresses, because if you look at the direction of the bending moment, it will bend the bending at H. At H we have tensile stress, and this mx will produce compressive stress. So when we put the value, applying method of superposition, so sigma y is 66 megapascal. Okay, so now for the shear stress, only Vz will produce, so Vx will be 0. Vx will produce, shear stress will be 0 due to Vx, and that will be tau Yx. So evaluating shear stress, first moment of area for this region, shaded region, we calculate, and T we know. So putting the value Vq over It, Vz Ix by T, so that will become shear stress is 17.52 megapascal. Means at point H, if we consider, so we have sigma y, that's a normal stress, and we have tau yz, that is our shear stress. Okay, now and the sigma x, let's take the other direction, sigma x, so sigma x will be 0. So we have sigma y, tau yz, these are the non-zero values. So in order to find the principal stresses, so that is basically radius tau max, that will become, so if we want to write, so that I will write sigma y by 2 square plus tau yz square, right? That is radius. So when we put the value, so that become 37.4 megapascal, and that is equal to my tau max as well. So maximum shear stress, sigma max, is equal to sigma average plus radius, and sigma average is 32 millimeter because 60 sigma y was 66 millimeter. So the half of that will be 33 millimeter plus radius, so 70.4 megapascal and 7.4 megapascal with the minimum. And obviously the sigma c is 0. Now the maximum shear stress in this case will be the radius of this circle because the nature of stresses is such that the sigma max is tensile and sigma minimum is compressive in nature. So that the maximum shear stress in this case will be in plane shear stress. And the orientation tan to theta p, either you can use this from the circle or you can use this relation as well. That was equal to 2 times tau xz, yz in this case, minus sigma y minus sigma z. So with that formula you can also find the maximum value of shear stress, theta p. Sorry, that will be give you the value of theta p. Tan theta p will be equal to this value. Okay. Now, in order to solve for the general case of loading, so first you have to take a section where you are interested to find the stresses. Then you will transfer your internal, you will find the internal force moment over there. It must have the equilibrium condition. Then you will find the stresses and apply method of superposition by considering the centroid principle as well. Then you will evaluate the maximum, you will find the principal stresses and maximum shear stress. Now, let's further clarify more things using this problem. This is two forces. Two forces are applied to a pipe AB. So as shown over here, two forces applied, 1200 Newton and 1500 Newton acting in this direction. So this is my x-axis, z-axis and y-axis. Knowing that the pipe has an inner and outer diameter equal to 35 millimeter and 45 millimeter. So this pipe, the inner diameter is 35 millimeter and outer diameter is 42 millimeter. Determine the normal and shearing stress at point A and point B. So currently we don't have to find the principal stresses, but we have to find what will be the normal stress and shearing stress at point A and point B due to this loading. Okay. Now, so if I take a section over here, passing through this point A and B, so what we have like this. No, sorry, excuse. Let me draw again. If you take a section, okay, now better. Hopefully it's better. Okay, we have a point A, let's suppose it's A, and we have a point B over here. So center, so this is my z-axis, my x-axis, and out of the page is my y-axis. Now, this 12 kilonewton force, let's see, first we have 115 kilonewton, 1500 kilonewton force, and that is along y-axis. Now if we want to draw it, So that will be a compressive force acting at the centroid of the section, and that will be equal to, let me write as a P, and that P is equal to minus 1500 Newton. Okay. Now the another force is this due to 1200 Newton, that is acting along z-axis, that is become shear force. So let me write Vz. So Vz, that is my shear force, is equal to 1200 Newton, and it's opposite direction to the positive, so let me put negative over here. What else? Now this, so let me change the color for the moment. So let me put this color. Okay, now this there will be moment about x-axis that will be equal to 1200 Newton multiplied by 75 millimeter. Means we have a moment about x-axis applying the direction that will be along clockwise direction. So the mx will be equal to the distance is 75 millimeter. So 1200 force negative and 0.075. So mx will become minus let me erase, minus 67.5. Newton meter. Now this 1500 Newton force multiplied by 45 millimeter, this distance will also produce moment about z-axis. And let me draw. So again, if you're looking at the z-axis, that moment will be clockwise direction. So mz, so we can write mz will be again negative. That will be 1500 Newton the force. The distance is 0.045 meter, and that mz will be minus 90 Newton meter. Now this 1200 Newton force multiplied by this distance. Now this distance will be 45 millimeter plus 45 millimeter on that top as shown over here. 45 millimeter, 45 millimeter, that will produce torque or moment about z y-axis or torque, and that will cause torque, and that will be, so let me change the color. Well, let's put this yellow color. So that will produce torque T, and we can write torque T is equal to 1200 the force multiplied by the distance. Distance is 45 millimeter, 0.09, and that will become 108 Newton meter. Okay. Now what else? We have a C outer, that will be 42 divided by 2, 21 millimeter, and inner radius is 35 divided by 2, that will be equal to 17.5 millimeter, or we can write 0.021 meter or 0.0175 meter. Okay, these are the radius. And what else we need? We need area as well. That will be pi C outer square minus C inner square And if we put the value, so that will become 423.33 millimeter square. I, since it's a circular cross section, so I will be pi by 4c outer 4 minus c inner 4. And if we put the value, so that will become 79.008 10 to power 3 millimeter 4. And j is 2 times I, so if you multiply by 2, so that will become 158.166 10 to power 3 millimeter 4. Okay, now let's take point A. What we have point A? Point A, we have normal stress. Let's consider normal stress, sigma A, sigma. So we have a normal stress due to force P. Then we have at A, due to moment about x-axis, what we have? We have due to moment about x-axis, we will have mx, and that will be causing normal stress at A, and that will be tensile in nature. So that we can write plus, or in the general form, let me write mxc divided by I. So putting the value, P we already know that is minus 15,500. Area we calculated, so we can write 423.33 10 to power minus 6, that is in meters, is equal, minus mx. Mx is minus, we have a mistake. So that mx is due to 1200. Yes, okay, right. So mx will be equal to, there is a mistake. So calculation mistake. So this must be 90. So this will be 90, and this value will be equal to 67.5. So my mistake. So I put the wrong value. Okay. Now what else? We have minus mx, so that will be minus 90. So we are finding at the outer radius 0.021 divided by value of I. Value of I is 79.083 10 to power minus 9. So sigma A will become, so if we calculate, so minus plus, so that will become 20.4 megapascal. Now the shear stress at A will be due to torsion Tc by J, plus we can say that that is due to shear force acting along x-axis Vx, and right, so divided by IT, since there is no shear force acting along x-axis, and the shear force along the z-axis is passing through point A, so that will produce zero stress. So that the shear stress at point A will be only due to torsion, and the torsion is torque we already calculated, that is 108. Outer radius is equal to 0.21, 0.021, sorry, not 0.21. So let me erase, Control P, 0.021 divided by J, 158.166 10 to power minus 9. So that will become plus 0 because there is no shear stress due to transverse load or shear load. So that is equal to 14.34 megapascal. Okay, now for point B, normal stress will be P by A. Now for point B, mx will produce is lying on the neutral axis for mx, so there is no shear normal stress due to mx, but there will be a shear stress due to mz, and as shown the direction over here mz, so that shear stress will be compressive in nature over here. So we can write like mz divided by c divided by I, and the nature of stresses will be compressive. Minus 1500, that's the compressive load, 423.33 10 to power minus 6, minus mz is 67.5, c2 is 0.021 divided by I, 79.083 10 to power minus 9. So when we calculate it, so that will become a compressive normal stress 21.5 megapascal. Now the shear stress in this case will be equal to, due to torsion plus due to shear force Vz divided by Q over IT. Why? Because Vz, now this is lying on the neutral axis, so obviously the shear stress due to transverse load will not be 0, it will be equal to VQ over IT. Now for the Q, we will take the half circle and we will calculate Q for this region. So over here we have a point B, and we are interested what is the shear stress at point B, so we have to calculate for the half circle. So this is a centroid, the force is passing VC in this direction, so we have to find what is the value of first moment of area Q for this region. Okay, now Q for semicircle, for this problem, let me put, so Q is equal to 2 by 3 C naught cube minus C I cube. So this is the value of first moment of area, half circle, half semicircle, a semicircle with a semicircle cut out. Okay. So the Q for this problem, if you put the value, so Q will become, if you put the value 2.6011 10 to power 3 millimeter cube. Okay. Now putting the value 108, 0.021 divided by 158.166 10 to power minus 9 plus VQ is 1200 Newton. The same direction, so as a as a shear stress due to torsion load, so the both will add. Okay, now the value of Q we already calculated over there. So 2.6011 10 to power minus 6 divided by I we calculated that was equal to 79.083 10 to power minus 9. And now thickness, so we are taking this semicircle region, so T will be equal to the thickness will be equal to outer 2 times outer radius minus inner radius, or the outer diameter minus inner diameter, so that is 7 millimeter. So 7 into 10 to power minus 3. So when we calculate, so this will become 19.98 megapascal. Now these are the value of normal stress and shear stress on point A and point B. Now if you want to calculate principal stresses, so you have to apply the formula for the principal stresses. The normal stress is known, the shear stress is known, so you can find the nature of stresses, and the maximum shear stress can be in plane or out of plane depending on the nature of principal stresses. So this is how you will calculate the stresses under combined loading. Okay, these are the assignment problem for the combined loading case. Please solve those problems, and you can also look at the concept application and the sample problem 8.4, the concept application 8.1, and it will further clarify your concept. And if you have any question and query, we can discuss in the interactive session as well in detail. Okay, thank you very much. The next lecture I will discuss not required for the course, but it is important topic, the failure criteria that you will study detail in your next course. But I will briefly explain few terminologies and what are the yield criteria, or when the yielding will start for the combined loading, for the ductile material, and what will be the failure criteria for the brittle material, in very briefly, but not in detail. That is not from your course, that is something extra, or something for very informative, and that you will use in the design of machine element course that you will study next semester, as well as the mechanics of solid 2 course you will discuss in detail over there. So thank you very much, and see you inshallah for the next lecture.